Hello, in this video I'm going to solve the following problem for you. Probability theory, convergence in probability. Let x sub n be a sequence of identically distributed random variables such that the probability of x sub n equals minus 1 is equal to 1 over 2n. The probability of x sub n equals 0 is equal to 1 minus 1 over n. And finally, the probability of x sub n equals to 1 is again 1 over 2n for every natural number n. Part A. Show that x sub n converges in probability to 0. Part B. Show that for every positive r, x sub n converges in r mean to 0. This problem is a rephrasing of exercise 1.2 and page 150 in the following book. Pause the video at this point and give it a try. Okay, before solving the problem, one observation is important to make here. If you add this number and that number and that number, then this result will be 1. So what does it mean? It means that the probability of xn for any n in n to take a value a where a does not belong to the set of minus 1, 0, 1 is indeed equal to 0. That is the conclusion that we make when we add these three numbers and the sum of them is equal to 1. It means that there will be no share left for the probability of other numbers if there are some, of course, outputs of this random variable. The statement of the problem is not in a way that guarantees that there are no other outputs for the random variable x sub n except minus 1, 0, and 1. So we have to consider this possibility into account. Okay, so now let us go to the first part of the problem. Part A. Okay, in part A, we want to show that a sequence of random variables converges to some other random variable, in this case mentioned to be 0, in probability. So let me remind you the definition. So let us say that I have a sequence of random variables x sub n, and I have another random variable x. We say that this sequence converges to x in probability, and we put a p on top of this arrow, if this definition is satisfied. For every epsilon greater than 0 given to you, if you calculate the probability of the absolute value of xn minus x for some value of natural number n, and consider this greater than 0 epsilon, this epsilon is the same epsilon that you have here, it becomes a number which depends on n. And then if you take the limit of that and then n goes to infinity, it should be 0. So if this is satisfied, then we say that this sequence converges to x in probability. Okay? But in our case, of course, we want to show that the given sequence is going to converge to 0 in probability. So it means that if you give me any epsilon which is positive, I have to convince you that the limit of p of absolute value of xn minus the limit random variable, which in this case is 0 and I don't need to write it, is greater than epsilon, is indeed equal to 0 as n goes to infinity. Okay, so this is what I want to show. Okay, but because of the statement of the problem, immediately it becomes clear that I have to discuss two separate sets of values for epsilon. So let me do it case by case. First, let me consider that this epsilon that we are given is greater than or equal to 1. Okay, and let n be any natural number. Okay, let us understand this number for this case. So let me try to be very clear for every step. Okay, so it might be goes a little bit long, but I think that you will have a better understanding of this. So what is the meaning of this set? This set in principle is a short form for the set of all omegas in the sample space capital Omega, such that absolute value of x sub n for that chosen n acting on omega becomes a number which is greater than epsilon. Okay, but let me actually draw some pictures for you so that you have a better understanding. So let us say that here this is the sample space omega, and here we have the set of all possible real numbers. Three of them are important for us. So one of them is number -1, the other one is number 0, and the other one is number 1. There might be some points here that are assigned to this by the random variable xn. There are other points maybe that they are assigned to 0, and there are some other points that are assigned to 1. So let us do it here, draw something here for you. So let us say that this set, all of these elements are assigned to -1 by the random variable x sub n, and I give it a name, a sub -1, for example. And there are other here elements from omega that are assigned to 0. I give it a name, a sub 0, and then something similar, for example, I will call it a1, and then assign to this. What does it mean? It means that if you pick any omega from here and apply x sub n on that omega, the output is -1 regardless of which one of these elements you choose. And the same story here, all of them are assigned to 0 and everything from here is assigned to 1. This is the picture we have. But we don't have any clue, okay? Might be, first of all, one thing that is clear is that all of this one and that one are disjoint, this one and that one are disjoint, that one and that one also disjoint. It's very clear by the definition of these sets. But it is not guaranteed that if there is something outside of these green sets left or not. So we have to consider that possibility into account. We cannot just rule it out, okay? Okay, so now here I am assuming that epsilon is greater than 1. And I am looking for all those omegas for which when xn acts on it and I take absolute value of the output, it becomes greater than epsilon. Okay? One thing is clear, this omega cannot be here. Because if this omega is here, it will be assigned to -1. Absolute value of -1 is 1. 1 cannot be greater than epsilon here, because the minimum value of epsilon is 1. For the same reason, omega cannot be here. For the same reason, omega cannot be here. But omega might be somewhere else, okay? We don't know. So we have to consider that. So what I am going to write is as follows. Okay, so if I ask you where you can find this omega, you will tell me that if there is such an omega, this omega should be outside these green regions. Okay, so what does it mean? It means that it is a subset of the complement of the unions of these three sets. Yes, so it becomes a -1 union a not union a1 complement. Okay, so then it means that because this set is a subset of that, the probability of this set, which I am interested in calculating, is less than or equal to the probability of this event. So this means that the probability of absolute value of xn greater than epsilon is less than or equal to the probability of a -1 A0 union A1 complement, but we know that probability of the complement event will be 1 minus probability of the event itself. And because these events are mutually disjoint, so I can write minus probability of A minus 1, probability of A0 plus probability of A1. Okay? But if I ask you what is A minus A sub minus 1, you will tell me that this is the set of xn to be equal to minus 1. Yes? And then if I ask you what is A0, you will tell me this is the event that xn is 0, and etc. Okay? And then we know that this is equal to 1 minus the probability of this is 1 over 2n. And then I have the other one, which is 1 minus 1 over n, and the other one is 1 over 2n. And if you do this calculation, it becomes 0. Yes, because here this one and that one becomes 1 over n, cancel that one, 1 minus 1, cancel that 0. So this means that this probability is less than or equal to 0. But of course, you know that the probability should also is greater than or equal to 0. So it means that probability of xn is greater than or equal to 0 is equal to 0 for any n in the set of natural numbers. So what does it mean? It means that this sequence, for at least this case, is the constant sequence consisting of all zeros as terms. And you know that if this happens, the limit of this sequence is also 0. Yes? Okay, so I was able to show that this is indeed the case, but if you give me epsilon greater than or equal to 1. But I have to prove this statement for all possible epsilons, so I have to consider another scenario as well. So let me take some of these things with me to the next page, and then we continue there. Okay, now we consider that epsilon is somewhere between 0 and 1. We again want to prove the same thing. Okay, and that's the picture that we had on the previous page. Okay, so again, I will start with the definition of this. So this is the shorthand notation for this set, but here be careful. I want to see where these omegas can lie, can be there, can be located, yes? So where can I find these omegas? Every omega in this set is acceptable because every omega in this set is assigned to minus 1, and the absolute value of minus 1 is 1, which is definitely greater than this epsilon here. So this means that if I want to write this, this consists all a sub minus 1s. But it cannot contain any element from here because these are assigned to 0. Absolute value of 0 is 0, and 0 is not greater than epsilon. Epsilon is greater than 0. So none of them is there. So let me cross it over, so none of them will work here. But now, what about this one? Yes, all of them are also acceptable because any omega from here goes to 1, and the absolute value of 1 is 1, so it is greater than epsilon. So this means that the next set is here. But there might be other places, other omegas somewhere else, that are also assigned to a number greater than this pre-assigned epsilon. So we cannot just rule it out. Let me call that set M. Okay? So what is M? M is consider this region outside all of these green regions. And from there, you find all possible omegas for which this is satisfied. Of course, this M might be empty, but this is not guaranteed. But one thing is clear, whatever this M is, this M is a subset of a minus 1 union A0 union A1 complement. It lies outside this union. So one thing becomes clear immediately, that the probability of that m is always less than or equal to this probability, but probability of the complement is 1 minus the probability of a minus 1 union a0 union a1. But we calculated that before, which is 1, so 1 minus 1 becomes 0. So this means that the probability of m is less than or equal to 0, so it has to be equal to 0. So that is the important point. Okay, now I go here and I calculate the probability of absolute value of xn greater than epsilon. This becomes equal to the probability of a minus 1 union a1 union m. Yes, but because these events are mutually disjoint, I can write it as probability of a minus 1 probability plus probability of a1 plus probability of m. Probability of a minus 1 is 1 over 2n according to the problem. The other one is also 1 over 2n, but the probability of m is 0, so it becomes 1 over n. Okay, but look, what I'm supposed to calculate, I am supposed to calculate the limit of these probabilities. So I have to take the limit of p of absolute value of xn greater than epsilon, n goes to infinity, but I just calculated this bit to be 1 over n, n goes to infinity, and of course this is again 0. So this means that in any case, if you give me any epsilon greater than 0, depending of the size of the epsilon that you give me, if it is 1 or greater than 1, or is it really between 0 and 1, I was able to show that in any case this holds. So then it means that xn approaches the 0 random variable in probability. Okay? So now let us go to the second part of the problem. Okay, for the second part of the problem, what we want to show that this sequence converges to 0 in R mean. And of course, R is a positive given number. So let me just review the definition. If I have a sequence x sub n, we say that this sequence of random variables converges to the random variable x in R mean whenever R is a positive given number, if I calculate the expectation value of the absolute value of xn minus the limiting random variable to power r, which becomes a sequence of numbers, and I take the limit if n goes to infinity, this becomes 0. Okay, and of course people don't write r mean, we just put some r up there. So my goal is also to show that xn goes to 0 in R mean. Okay, so I have to calculate this. Okay, so let me calculate E of absolute value of xn. Here I have already chosen my n, and then minus 0 and to power r. This becomes a number. I have to convince myself that the limit of this number, if n goes to infinity, becomes 0, but this is equivalent to saying that the limit of E of absolute value of xn to power r, n goes to infinity, is equal to 0. So that is what I want to show. But that's very simple because this is a discrete random variable, so I can write the formula for the expectation value. So this becomes every possible output for this combination multiplied by the probability that this output occurs. So in principle, one of the possible values is minus 1, so this becomes absolute value of minus 1 to power r, but multiplied by the probability that xn is minus 1, plus the other possibility is 0, so it becomes absolute value of 0 to power r, probability that xn is 0, and then plus the other one is 1 to power r, probability of xn equals to 1. But there might be other possibilities which I'm not sure which numbers are there, but I don't need to know them because I can write it collectively as a sum of absolute value of x to power r probability. Let me write a probability of xn equals to a if a is not equal to -1, 0, and 1. Okay, so let us calculate this. So here, this is just simply 1, and we already given that, which is 1 over 2n. Okay, this is 0, so this is cancelled. This is 1, and this is exactly 1 over 2n again. Okay, even though I don't know other values, but I don't need to know. In the beginning of the video, I told you that based on those numbers given, probability of this happens if a is not one of these numbers is 0. So even if I don't know what a's are, because all of them are 0, so this sum will vanish again. So this means that this becomes just simply 1 over n. So it means that the expectation value of absolute value of xn to power r is just 1 over n, and now I take the limit. Absolute value of xn to power r, n goes to infinity, so that also becomes 0. So I was able to answer this question mark positively, and it means that I am done. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.